All right, we have the Chapter 13 Math Analysis Practice Test. So let's go through some of these and see if we can do them. So we have a first question, right, in summation notation, right? So that's using the sigma. All right, so there's a few parts of sigma. We usually start on the first term, right, when we're doing series of sequences. We have to know how many terms there are total, right, or if it's infinite. And then we have to have the a sub n term right here, right? So we have to know what that is, right? And that'll tell us if we plug in 1, we should get an answer of 5. We plug in 2 into this expression, it'll give us 9. We plug in 3 into it, will give us 13. And we plug in the last number, whatever that is, it should give us 65. So we got to do those two things. Of the two, well, to find the a sub n, you actually need to know what n is in the formula. So we need to start with just finding out with how many terms. So you could just say, you know, figure out that this is a difference of plus 4, right? And you can keep on going plus 4, plus 4, plus 4 until you get to 65, and then find out when count how many times you did plus 4, and then you'll know how many terms there are, right? You could do that. That'll take a while. So instead we like using the formula a sub n, right? Make sure you use arithmetic, right? So, and that's going to be equal to whatever the first term is times however many times you multiply by that difference, right? Well, 1 minus n minus 1 times the time, how many times you do it, right? It's always n minus 1 because when you're doing this, you're actually going to add 4 one less time than how many terms there are. So if there are 10 numbers here, you only have to add 4 9 times to get there, right? That's why it's minus 1. So let's plug in what we know. We got 5 for a sub 1. We got, well, we know our difference is 4, so put that in there. And our a sub n, which is our last term, we know what that is, so we can plug that in. So 65 is our last term. So now with this, we got everything filled in except what we're trying to figure out, n, right? So just solve this. We got 65 equals 5 plus 4n minus 4, right? Simplify this a little bit. So we got 65, 4n plus 1. So we got 64 is equal to 4 times something. And if we divide both sides by 4, we'll get 16. There it is. So we got 16. Okay. All right. So now we can find out what a sub n formula is. So we have 65, but we're not going to plug that into this time. We're just going to plug in everything on the right-hand side. So a sub n is going to equal 5 times n minus 1 times the difference. So I left the a sub n out and the n out. Anything with n. I just put in the first term and the difference, right? So we got 5 plus 4n minus 4. And it looks very similar to what we just did over here. Right? 4n plus 1. So that's what our a sub n is. And you can check it, right? You can plug in, let's do this just to make sure. Plug in 1, right? Do you get the first term? This is a sub 1, right? So if you plug in 1, you should get 5. 4 times 1 plus 1 is 5. And a sub 2, right? We should get 9. So plug in 2. 4 times 2 plus 1 is 9, right? So you can always check it. You don't have to wonder or guess and hope you got it right and wait for it to be graded. All these are very checkable before you even turn it in, which makes it a very nice assignment to get a good grade on. So I'm just going to erase that, and in its place I'll put the actual a sub n. Right? And there's lots of ways of doing this. You see how I did it, but you might figure out a different way that also gives you this. Some of you might look at this and just kind of like, no, well, I know it's, they're 4 apart, and if I just start at 1, and it might just work out, that you can figure it out, which is fine as well. Okay? But just show your thinking no matter what you do. So that's our first answer right there. Oop, that didn't work. That's what I was going for. All right. So let's go down and do write a definition of recursive sequence. Okay, a lot of people miss this on the quiz just because of a vocab issue, right? So if you don't know what this means, or understand that there's actually 2 different ways of writing these sequences down, you might have picked the wrong way to do it, right? So we want to not do that. We want to pick the right way. So let's go how about we know what the format looks like? So it's two parts. You have to have what the first term is. That's always a good thing to put down right away. It's the easiest part of the problem. And then here we're going to have to say every term is going to be related to the previous term. So you're going to have some previous term, right? Like, and we denote that by saying a sub n minus 1. All that means is the previous answer. So we're trying to come up with a formula that says just take the last number we got and do this to it. So if I'm trying to figure out 6, what did I have to do to 2 in order to get 6? My last answer, I have to once again, let's see, is it add 4? Well, it's got to be the same thing here. So since add 4 doesn't work here, 6 plus 4 is 10, not 18, so that's not it. So you're just figuring out what we're actually doing here. So we can try geometric and say maybe it's times 3, and sure enough, that's what it is. So to get the next term, all I have to do is take the previous term and multiply it by 3. So my formula will just be, well, take 3 times whatever the previous answer is, and that'll give me my new term. All right, so that's the format for recursive. You got to have the a sub 1 step. You got to have a sub n step. Right? These two things will always be like this on the left-hand side, and then the a sub n step, you will have an a sub n minus 1 somewhere in there. So this could be 3 times something, or it could be this plus 3 or divided by 3, but that n to the a to the n minus 1 will be there somewhere. Okay? So straight up question. All right, now let's find the sum of some terms. Again, we could go through and find out what the difference is or the ratio is and just come up with all the numbers up to 9 and then manually add them all together, which if you had the time and a calculator, that would be a good way to check. But you want to show your thinking and show it formulaically. So we have to know first which formula to use, arithmetic, or is this the geometric? So we just look at this, and one clue here is that it's switching from a negative to positive, and so on, back and forth. So that can only happen with the geometric, right? So we have here, I think it's just got to be what? Multiplied by -2, multiplied by -2, and so on. So I have a ratio, an R, right? So you got to use a formula with an R, and that has an S in it, right? So that's the clue. If you have a list of formulas given to you, like you were on the quiz, you'll know which ones to go towards, right? So my equation is going to be, right? And I can actually put 9 because I actually know it's the 9th term. My sum is going to equal, right, my first term, which is -5, 1 minus our ratio, which is -2. So we'll put that in parentheses. And we know it's 9 terms, so it's going to be to the 9th power. All divided by 1 minus r, which is, again, be careful, 1 minus negative. So let's simplify, clean it up, and see what the answer is. So we'll have 1 minus -5 times 1. Let's see here. This is going to be, my calculator says this is 512. Negative, right? But I'm going to have a minus and negative, so that's going to be plus 512. Just using a calculator. All divided by 3. And we got, simplify, of course, was it 513, which 3 goes into evenly because 3 goes into 51 and 3 goes into 3, so I know 3 goes into 513. So check on a calculator, and that is 171, which now calculator again, you get negative 855. Yeah, there we go. And it makes sense that it's a negative, right? Because it looks like the odd terms are the minuses, right? So the first term is a negative. The third term is a negative. So the last number we know here is going to be a negative number, the biggest number so far. So it makes sense that that's why it's negative. Because it's bouncing back and forth between positive and negative. But since the last one's negative, the sum ends up being negative. All right, now let's look at doing some neighborhoods. All right, so we have to determine what the lower and upper bounds are, right, from this. So this is like a, remember the radius is kind of like a plus or minus, where this is like the center, right? So we're going to go from 4, go down 0.01 and up 0.01, right? So we come up with our two values. So we're going to have, what's that, 3.99, right? We'll get less than our function, 1 plus 4n squared divided by n squared, less than 4.01. Now I just need to solve each one of these separately, right? So let's do the first one here. Solve that. So we have 3.99. I'll just rewrite this. And we can start by multiplying both sides by n squared, right? Which can effectively just move that right here, right? So now I have 3.99 n squared is less than 1 plus 4n squared. And let's get these n squareds together. So subtract 4n squared on both sides, and this will come out to, what is it, negative 0.01 n squared less than 1. And divide both sides by that exact number, which is 1/100th. If you look at that, 1/100th. So we'll have n squared is now greater than, divided by negative. So n squared is now greater than 1 divided by negative 0.01, which is equal to negative 100. So not really useful to us, right? A negative number, remember, and we have to take the square root, which square root of a negative, that doesn't work, so we can just abandon this route and then look at the other one. So that's definitely inconclusive, does not help us. So let's look at this other side. Hopefully that's more useful. All right. So we got same steps, more or less. All right. So I multiply by n squared. So I got 1 plus 4n squared minus 4.01 n squared. Subtract 4 on both sides, 4n squared on both sides. So now I'll have, once again, 0.01 n squared. And I don't have a negative here, so that takes care of that problem. So divide both sides by the 0.01, or 1/100th, right? So 1 divided by 1/100th will give us 100. And now we can take the square root. Yeah. And technically, yeah, square root of both sides, you get a plus or minus, but again, this is a natural number, right? There's no such thing as a negative natural number, so we just leave it as that, positive only. And of course, I think it says which terms are in the neighborhood. So 10 is not in the neighborhood. That's at the gate, right? So our actual answer is going to be everything bigger than 10 that's a natural number, which means it's going to be 11 and up. So the way we write that is equal to and greater than equal to, and that's the answer you want to have. Those are all the terms that are going to be inside the shaded area if we graph this. All right, let's keep going. Give the first 4 terms. So this is the recursive formula, and it looks like, well, let's go back here. Remember how I said it has to have this a sub n minus 1? Yeah, this doesn't have it. A little typo. So I spotted that right away, because this type of method does not work unless you have this n minus 1 here. All right, so we got to have that. Otherwise, it's saying to get this answer, right, that you don't have yet, use the answer that you don't have yet and then add 1 to it, which seems ridiculous, right? So that's why this has to be, no, I need the previous term. I need the previous answer. I'm going to add 1 to it. That'll give me my new answer. So without that minus 1 there, it's kind of gibberish. So all it's saying is like, okay, my first term is going to be 1/3. It says right there. And my next term is going to be 1 more than that. It's going to be 1 1/3. And I can keep on going till I get 4 terms. So this is something that's quite easy to decipher. We're just going to add 1 a couple more times and we'll be done. It doesn't say to add them up. It doesn't say to do anything else, but just list them. So I think that's it. Yeah. All right. Let's keep going. Let's state the general term, all right, of the sequence. So here we can see if it's arithmetic or if it's geometric, or if it's neither, we just have to kind of break it down to smaller parts. Okay. So looking at this, like from 2/3 to 3/4, is at the same distance from 3/4 to 4/5. Like, no, these are smaller fractions, so they're getting closer and closer together. The difference is not going to be the same. Same thing if you try to multiply. You can't really multiply 2/3 times 1 because, that doesn't work either. So this is something we're going to have to look at piecemeal, which means we're going to figure out a pattern just for the top, right? And see, what if I plug 1 into what formula, it'll give me 2. If I plug 2, it should give me 3. If I plug in 3, it should give me 4. All right? So really, all we're doing is saying, well, whatever number you're given, the n, you just need one more than that, plus 1. All right? So now if I plug in 1, I get 2. I plug in 2, I get 3, and so on. And then I can do the same thing for the bottom. The only thing is that I need to plug in 1 and get 3. I need to plug in 2 and get 4. Right? So similar, but I just need to add 2. So 1 plus 2 gives me 3. 2 plus 2 gives me 4. 3 plus 2 gives me 5. So this is my general term, or my a sub n here. Will equal this. So notice where we did not use the formulas. We did not, have to go too deep. We just had to do pattern recognition, and that was it. All right, let's scroll on down. All right, so let's find the sum of this one, right? And we got to recognize that we're starting at 0. So we're going to plug in 0 first, and then plug in 1, 2, and 3. 4 numbers, right? Even though going to 3, we have 4 numbers total, because we're starting at 0. And to find the sum, since it's a little complicated, all we're going to do is just plug in 1 number at a time and see what we get, right? So let's do it this way. Let's first plug in 0. So we got -1 to the 0. We got 0 plus 1, and 2 times 0 plus 3. All right, we'll find out what that equals. I'm going to write these all out first. -1 to the first, 1 plus 1, 2 times 1 plus 3. Find out what that equals, and then keep going. -1 to the second, 2 plus 1, and 2 times 2 plus 3. Find out what that equals, and let's just go gray. And then we have our last term, which is to the third power. We got 3 plus 1 times 2 times 3 plus 3. All right. So let's just start here since we got that. So we got -1. From -1 to the third power is -1. And then we got times 4. And then we got 2 times 3, 6 plus 3 is 9. -36. Right there. Let's work our way up. So here we'll have +1, because it's -1 squared, so we're on positive, times 3. 2 times 2 is 4. 4 plus 3 is 7. Right. And let's go up one more. So we got -1 to the 1, so we're back to -1. Right. And we got a 2. And we got, I'm guessing, 5. 2 times 1 plus 3. So you'll notice that by stacking this work, I can actually see a pattern from here to here to here. So if you wanted to, we can just keep following the pattern, negative, positive, negative. Okay, that's going to be positive. 4, 3, 2, 1. 9, 7, 5, 3. Just counting down by odds. And then check the work, and yeah, it works out that way. So quite beautiful. Nice, elegant answer. And forgot to actually multiply these. We got +21, and we got negative 10, and the first term, 0 term here, which is 3. So we have 3 minus 10 plus 21 minus 36. Add those all up, and you get, all right, calculator time. Let's see here. Negative 22. Yeah, I think the sum equals negative 22. All right. Voila. All right, let's find the limit, number 8. So this is a polynomial. So by the definition, we can just go through and divide all the terms by the highest degree. In this case, the highest degree would be n to the third. So I'm going to divide every term by that. So let's first rewrite it, give me a little room to work here. All right, find this limit, which means what happens to it if we graphed it out and went to the highest number we can think of. What does it do? Does it diverge? Does it converge? If it converges, to what number? All right. So let's rewrite this, leaving some room underneath and a little more space. And again, the highest degree is to the third, so I'm going to divide each of these by n to the third. All right. And ask myself, what happens to each of these numbers, right? What happens to each number? What does it equal if I would make the n in it, wherever it is, infinitely big? So you can, think of just the biggest number and ask yourself what happens. So 3 divided by any huge number, right? That's going to become a very, very small number, so small it's basically equal to 0. All right, so that first term just turns into a 0. Same thing here, even though it's going to be 1 n on top, we'll have an n squared on the bottom, so it's 1 over n squared. Still, if I make this n infinitely big, that also becomes 0. Right? And so on, we just keep doing that process. Same thing here, if I do this, right, 2 of those will cancel out one of them, and I still have an n on the bottom, right? So negative 2 divided by some huge number will come out to basically 0. All right, so far, just a lot of zeros. Over here, we have n to the third divided by n to the third is just 1. So that actually equals 1. And then right here, we're back to the same thing. We have basically the same thing as over here, divided by n to the third. That's going to be 0. So in the end, we have 0 over 1, which just equals 0, which means it converges to 0. So if we plotted this and graphed this, right, it looks something probably like this, like a horizontal asymptote, right, going towards 0, closer and closer and closer, but never actually crossing it. Converges to 0. The limit equals 0. As far as it goes. It doesn't go any lower. All right, let's go back to some sigma notation. A little practice here. So let's get that ready. We're just going to write the a sub n term here, so we know it's going to start at 1. And 1, 2, 3, 4 terms total. So I got a 4 on top. That was easy. Didn't have to use a formula or anything to find it this time because it's very small. And we can see arithmetic, geometric, or neither. And looking at these numbers, I don't really see a pattern between 2/3 and 7/6 and 12/9. So break it down to smaller parts, and you do see a pattern because you look at just the denominators. Oh, I'm going from 3 to 6 to 9 to 12. Well, that's just times 3. That's geometric, right? So I'm going to have 2 rules. I'm going to have 1 on the top, 1 on the bottom. So I know that to get the bottom number, I just plug in my n and multiply by 3. So 3 times 1 gives me 3. 3 times 2 gives me 6. 3 times, you can always check it. And then do the same thing for the top, but just ask yourself, how do I get from here to here, here to here? And you can clearly see there's a difference of 5. So the top is arithmetic and the bottom is geometric. See how we snuck both of those into one question? All right, so I got to figure out, well, what can I plug 1 into? It gives me 2. And I plug 2 into it, it gives me 7. So you might be able to come up with it. You might see how to do that. Right? If not, just use what we did on one of the first questions. Right? Say my a sub n is going to be 2 plus n minus 1, and I know the difference is 5. Right? So we get 2 plus 5n minus 5, which is 5n, was it minus 3? That's what we came up with, and then check it. Right? Check it. So plug in 1, we should get 2. So we plug 1 in here, 5 times 2, no, sorry, 5 times 1 minus 3 is 2. That checks. Plug in 2, we should get 7. 5 times 2 is 10. 10 minus 3 is 7. Okay, so my formula does indeed work. Okay, and there you have it. That's our sigma notation. All right, let's keep on going. We have our find the limit. Oh no, find the sum. Yeah, I guess we're not finding it. Yeah, find the sum if it exists, right? I know it's a sum because it's a sigma sum notation, right? So it's kind of implied in the, by using this, we're adding things up. Okay. And if it exists. Now, how would it not exist? So we have to go back to our criteria for adding up. Oh, by the way, we should note that this is an infinite, right? So we have a formula right here that adds up an infinite amount of terms. But there's criteria. There's 2 of them. 1, this is only geometric. There's no arithmetic infinite formula. So it has to be geometric. Okay? Which means an r exists. And then once we get that r, that absolute value of that r has to be less than 1. Right? Now, why? This should make sense. Because if you're multiplying by, let's say, a number bigger than r, like times 2, like 2 times 2 times 2 times 2, that's going to diverge. It gets infinitely big. But if it's a small number, right, like 1/4 times 1/4 times 1/4 and so on, infinite amount of times, that gets smaller, 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 and actually will converge to, let's say, 0 or some very small number. So it's imperative that we check this first and don't just immediately use the formula without knowing that. Okay? So what is it geometric? And find r, and if it is it less than 1? So you might look at this and say, I'm not sure what to do here. Because all these other problems, like, oh, I have the terms. Like, I can see, oh, it's geometric because I can see multiple times 3 times 3. So when it's written this way, it's easy to tell, you know, what you're working with. So let's do that. Let's plug in 1 and see what the first term is. Plug in 2, see what the second term is, and 3 and 4, and then we'll hopefully see a pattern. Okay, so my a sub 1. Okay, I'm going to plug in 1. You notice that the pi just kind of hangs out on top. It doesn't really interact with anything. It's just there for decoration. And then we'll have 6 times 1 minus 1. And let's keep going. Plug in a sub 2. Again, pi hangs out on top. Now we're going to have 6 over 6 to the 2 minus 1. And maybe just do one more. Do our third term. Pi on top. 6 times 6 to the 3 minus 1. Alright. Let's see here. Let's simplify this, and just out of experience I know if I'm trying to look for a pattern, I don't really want to get what this numbers equals. Like I could find out, okay, 6 to 3 minus 1 equals 2, which is 36, but really it's more important that it's 6 to the second power. Right? This will be 6 to the first power. This will be 6 to the 0 power. So you see how it's easier to see the pattern if you don't actually multiply, 6 times 6 and get 36. Right? You can just tell, oh, to get from here to here, I'm multiplying by 6, right? But since it's on the bottom, it's really 1/6, right? Because the top doesn't change. To go from pi to pi, you're multiplying by 1. So my r here is going to be 1/6. Alright, so now I determine it's geometric because 1/6 works several times, so I got that. And yes, 1/6 is less than 1, so yes, I can use this formula. So let's do that. We have my first term, which is a sub 1, we know is pi over 6 to the 0, which is just 6. 6 to the 0 is 1, so my first term simplified all the way is pi. So that goes on top. Pi, once again, right? On the bottom, 1 minus 1/6. And then simplify that, so we have 5/6. And we can multiply top and bottom. Top and bottom here, and then we got pi times 6/5, so you can write that as 6/5 pi, or 6 pi over 5, same exact thing. So either one of those works. All right, so yeah, if we do this an infinite amount of times, which is quite interesting, all right, not just a million or a billion or a zillion or whatever, but forever, and it just adds up to that little number right there. All right, so here we go. Show all the terms behind a certain point at a general neighborhood. All right, so now we got, and then around its limit, right? And if epsilon is 1 over 1,000, which terms are in the neighborhood, right? So this is going to be a very, very small shaded area, so I'm guessing my n is going to be rather large. So recall, let's see here, zoom back in, that to do this, you need to know what the limit actually is, right? So the format is a sub n minus L is less than epsilon. This is our a sub n, right? We got that, but we don't know what the limit is. So we actually really have to do what we did up there in other problems and go through and see what the limit is. So that's step 1. Then we can do the rest of it. Okay, so the limit as n goes to infinity, right, of this, leave a little space, divide by the highest term, which is just going to be n's all around, right? So we have a couple of these cancel, so we just have that and that, right? So we have a 3 on top, a 4 on the bottom, and this one doesn't cancel, so we actually take that to the infinity, and it becomes 0. So our limit is going to be equal to 3/4. Okay, so got to have that part. Now we can plug that in here. I have my a sub n, I got my limit, and we can solve a little bit. Whoops. There we go. Okay. So now we have absolute value, which is really distance. In the higher classes, we really don't say absolute value a whole lot when we're actually writing these. Instead, we say the distance, because that's what it really means. The distance from here to the limit, to its limits. So, and we got to make that very, very small, less than some epsilon, which later on we'll plug in and find out. All right. So if we're graphing this, just so, all right. So it's probably doing something that looks something like this, right? And it starts leveling out. We know the limit is 3/4, right? And we have this small, 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 tiny shaded region, right? Small, 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 and we're trying to figure out when do these blue dots actually go and enter inside of here, right? With this only being what, 1/1000th, right? 0.0001. So very, very small. So it's going to take a while for it to get there. That's my guess, right? And it can technically come from the top or the bottom, but we can see it's going to come from the top, but we're going to write it out. So it could be negative epsilon down there at the bottom. Could be there. And at the same time, I'm going to be simplifying this. So it's 3/4, but I need a common denominator. We got n, and this is 4, so I just need an n top and bottom. Right? So if I simplify this, oh, sorry, that's minus. Oopsie. Oh, that's too big. Well, let's just make it bigger. Yeah, This is a minus sign, subtraction, because that's the distance between two things. So we have a 3n minus 3n, so we're just left with 1 over 4n, which is very workable here. Alright, and so we have to solve each one just to make sure. And as you can see here, if I solve this, I'll end up with, let's see here, n is greater than 1 over negative 4 epsilon, which doesn't make sense, right? Because n is a positive natural number, right? We can't have negative if n is a natural number, right? Because n stands for, that's the first term, that's the second term, that's the third term. There's no negative terms over here. There's no such thing as the 1.5 term. So we have to understand that this is a natural number when we're doing this, so we don't accidentally put a decimal answer or something like that. This is telling us when, at what of those numbers do we finally get inside this shaded region. It has to be like the 50th or the 75th or 100th or something like that. No decimals, no radicals. So that didn't help us, so we look at the other side. And you can kind of tell, you'll get into this more and more, but you can kind of tell, well, negative epsilon's down here, right? That's the negative epsilon. That's this bottom part. Well, we already kind of know that it's not going to, if you know how to graph this, you already kind of know it's not entering from the bottom, right? It's not going like this, so we didn't really expect that to give us any information anyway, right? We kind of know it comes from the top and goes like this, so it's going to be the positive epsilon. So we look at the other side. So that's 1 over 4n is less than epsilon. I'm just taking this part right here and solving it. And sure enough, epsilon must be greater than, that's n. There you go. N must be greater than 1 over 4 epsilon. Okay. Now that I have this, this is when I can say, let's plug in this epsilon and see how big this has to actually be. So the general rule here is that a small epsilon, if this is like really big, epsilon's really big, like say it's this wide, right? It takes up this whole area. You can see how this, well, it got in here like on the third term right away because it's so big. But if you make epsilon really, really small, it takes longer and longer and longer before it actually gets inside. So making it 1/1000th, like super, super small, it's going to be a bigger n. It's going to take a while for it to get up there. So now we can say, let's take this 1/1000, right, and plug it in for epsilon. All right. We have, let's see, 4 times 4 divided by 1,000. It's going to be 1 over 250. Right? Of course, 1 divided by 1 over that is just going to be the 250. Okay. All right, so that means back here, I'd actually have to go 250 of these before I actually get inside because it's so, so small. Okay. And it says if epsilon equals, I'm going to try to read directions so I make sure I answer the question. It says which terms are in the neighborhood? So 250 gets us to the door or the gate. So that means the terms that are actually inside, it's going to come the very next term after the 250th, which is the 251st, right? N will have to be equal to the 251st. But of course, all the terms after that are also in the neighborhood. It doesn't jump back out, so it's the 251st and everything greater than that. So that's why it's greater than or equal to. And that's the answer you want to have. Right there. Okay. All right, so there's quite a few steps on this. We had to find the limit first because you have to recognize first if it's not given to you, you need that to do this whole work, right? So you'll notice again in the math that you guys are learning, it's about understanding what you're doing, and just simply trying to memorize steps will only get you so far, right? And this is just the beginning. So do your best to understand what's happening so that if you look at this right away, you'll be like thinking of a graph and you're like, oh, wait a minute, I don't know what this number is. There's no way for me to do this problem if I don't know that, and now let you know that the first thing to do in this problem is to actually find what that limit is, right? But without understanding what's going on, you're just kind of like, well, do I just plug in, you know, I see a number over here, maybe I should just plug that in and see what happens, and, you know, randomly, hopefully I get lucky. Like, that kind of approach is not going to work very well, okay? So it's quite different. Takes practice, but just keep at it and you'll finally get it once it clicks, okay? Alright, lastly, let's do some induction, one of our favorite things. So we're trying to prove that this formula actually does add up all these, and the way we do that is say, well, let's add on another number right after this one and see if it works as well, right, abstractly. So the first thing we want to do, of course, is show that it kind of works just for, you know, the first term. So I should be able to plug in, since it's a sub 1, if I plug in 1 into this, it should give me this answer of 1. So all I'm doing is verifying. If I plug in 1, I actually get the answer that it shows right here. Because if it doesn't, then we got nothing to do. So good on your arithmetic. Of course, we get 1 over 1, which is 1. So that checks out. So then we have to do the next step, and you do need to write this out, the P, which we say, okay, we tried 1. Let's just assume P sub k, no matter what k is, 1, 2, 3, 4, 5, any finite number, it's true. Assume it's true. It works. So we can go through and plug in 2, and see if we get 1/2. We can plug in 3, verify we get 1/4. We could do that, but just for argument's sake, we're going to say step 2, let's just assume it's true. And let's see, on step 3, we're going to show that the next number, whatever number you pick, the next number after that is also true as well. Right? And here's how we do that. Switch it up. So I have my series here, right? And what, oh, I'll do k. And what is the next number after this one? So if I increase k by 1, right, I'll have the next term, which will be 1 over 2, and I'll put it, the next term after k is going to be k plus 1, and minus 1. And that, if I have a new term here, right, that's going to be the same as if I plug in k plus 1 into here. So it should add up by k plus 1, 2 to the k plus 1, minus 1. Change colors here. But, so I'm just taking k plus 1 and plugging in each one of these. Be careful to note what's actually in the exponent and what's not. So this minus 1 is just a regular minus 1 constant. It's not in the exponent, while the bottom it is. So if you're not super clean on your handwriting, you might think, oh, this is an exponent or this isn't, and you know, everything goes off the rails. So we already know, here's how we do this, we already know, this tells us right here, you know, this right here is exactly the same as this. So by the original formula that we already assumed is true, that this part actually equals this. We're just going to put in k's instead of n's, but that's it. Right? Then we have this new term we're still adding to it. Let's simplify it as well. 1 over 2 to the k plus 1 minus 1 is just 2 to the k. And then it should equal this right-hand side. And just recopy. The top and the bottom we can simplify. K plus 1 minus 1 is 2 to the k. So we got to combine these two on the left, and hopefully it comes out and equals this thing on the right. Both sides have to be the same. So the question is, well, it's a little bit different. Like, how do you find common denominators with powers? And it takes a little thinking about it. Like, what can I do to this 2 to the k so it's k minus 1? Or what can I do to this 2k to minus 1 so it turns into 2k? And since these are fractions, you should be thinking common denominators. You should be thinking, what can I multiply top and bottom? So the key there is multiply. What can I multiply one of these by to get the other? Right? So here's where the analysis starts of the class, the math analysis. Right? Well, if we have k, this is k minus 1. If I want to get k, this is basically has 2 to the k, but it just has this minus 1. So if I didn't have that minus 1 there, right, I would be good. So the question becomes, well, how do I get rid of this minus 1? On this problem, but also in general, what cancels out a minus 1? Well, I need a plus 1. If I had a plus 1 somehow, and I added a plus 1 here, that would work. Now, we can't just do this. Right? That doesn't work. That's not mathematically sound. But I could just say, well, how about I have an exponent of 2 to the 1, and I multiplied it. Right? Because remember, when you deal with exponents, if you multiply, you add these together. So really, this is going to be now a 1 plus k minus 1, which will cancel out. So with all that analysis, the answer just comes down to, just multiply top and bottom by 2. Right? If I multiply this by 2, right, I end up with 2 to the 1 plus k minus 1. Right? Add the exponents together, which equals just 2 to the k. So that's how I get all these under one roof. Multiplying by 2 or 2 to the 1. Right, so what do we get? We know we're going to get 2 to the k, which is good news. So now I got that. So my hope is when I simplify everything on the top, it just comes out to this. Alright, so one thing you got to be careful on. We're multiplying the whole numerator by 2. So if I'm not careful, I might just say, well, 2 times 2 to the 1 times 2 to the k. Well, that's just 2 to the k plus 1. And then we have a minus 1. And then we got a plus 1 over here. Uh-oh, those cancel out equals 0. Oh, maybe it's disproved. Maybe it doesn't work, right? Because it's not coming out to this minus 1. It's coming out to 0. But that's when you got to remember that we're multiplying the entire numerator by 2, not just the first term. So now it's distributive property. I get that. 2 times negative 1 is negative 2. And now when I bring down the plus 1, right, this will actually simplify to 2 to the k minus 2. And negative 2 plus 1 is negative 1. And I have proven, because both sides are identical. Check. All right. So a lot of things to practice. Make sure you can do all these problems and go back and do these old induction problems that we did last week. Practice them, redo them until you can do them all without stopping. So that's the golden rule, especially with mathematics. If you have a review, it's great to watch a video and see it and say, I get it. But after you do that and you write all the answers down, do it all over again and make sure you can do it by yourself with no help. Right? And do it as many times as you need to until you can basically come up with this answer key just like I did. And then, and only then, will you know for sure that you're ready. Okay? So put the time in and good things will happen. All right? Okay, good luck.